Right, so welcome back. We ended here, I think, in the last lecture. In this lecture, we're going to be talking about one more property of vectors, and then from that, we're going to go and jump to talk about matrices, and then talk about how you invert them and some applications in machine learning. So the last component I would like to discuss here is what we call a linear independence of vectors. So imagine I give you a collection of vectors v1, v2 up to vn. We will say that those vectors are linearly independent if you can construct a linear combination of them to be equal to zero if and only if the coefficients of that linear combination are zero. So in other words, if I have a collection of vectors, v1, v2 up to vk, we will say that those vectors are linearly independent if alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha k vk is equal to zero when alpha 1 equal to zero, alpha 2 equal to zero, and alpha k equal to zero. So we will call those vectors to be linearly independent in this case. And please notice that when you multiply alpha 1 by v1, you will still get a vector where the components of that vector v1 are just alpha 1 multiplied by the components of the vector of the original vector v1. And similarly, alpha 2 v2, if you multiply alpha 2 by v2, you will get another vector, where now the new vector will have components as alpha 2 times v2 1, alpha 2 times v2 2, alpha 2 times v2 3, and so on. And now notice that each one of those v's is a vector, right? So we're working in some Euclidean space. And from here, we can actually try to add them together, do this linear combination. And notice that the result of this linear combination is also a vector. That's why on the right-hand side, when we use zero, we are adding zero with the bold notation, meaning that this is a vector of zeros, right? So now you can only make this linear combination, alpha 1 v1, alpha 2 v2 plus alpha 2 v2 plus alpha 3 v3, and so on up to alpha k vk equal to this zero vector if each of those components, alpha 1 is 0, alpha 2 is 0, up to alpha k is 0. Now, a set of linearly independent vectors that are working in Rn are the basis vectors E1, E2, E3 up to En. E1 is the basis, is the first basis vector, and that E1 is made of 1 and zeros everywhere else, and E2 is made of 0, 1 and zeros everywhere else, and E3 is made of 0, 0, 1, so 1 on the third component and 0 everywhere else, and En is made of zeros everywhere except 1 on the last component. So we are working in a n-dimensional Euclidean space. We have n-dimensional vectors E1, E2, E3 up to En, and we have n of them. Each of those vectors, so E1 is defined as 1 on the first component, 0 otherwise. E2 is defined as 0, 1 on the second component, 0 otherwise. And En up to En, where En is defined as 0 everywhere except 1 on the last component. Now, those vectors are linearly independent because you cannot construct a linear combination, so you cannot find alpha 1, alpha 2, alpha 3, up to alpha n, such that if you sum those alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3 plus dot 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 plus alpha n En to get them to 0, unless you choose alpha 1 E2, alpha 1, alpha 2, alpha 3 up to alpha n to be equal to 0. Now, because those vectors are linearly independent, then we can write any vector in that space as a linear combination of those vectors. Because they are linearly independent, then any vector in Rn, remember we are working in Rn in this example, so any vector in Rn can be written as a linear combination of those vectors. So here's an example in R4 or a four-dimensional Euclidean space. So now if I'm working in R4, right, then you will have E1, E2, E3, E4. So you'll have four basis vectors. And each one of those is four-dimensional, right? Similarly, when we were working in Rn, we had n-dimensional Euclidean, n-dimensional vectors, and each vector was made of n components. Now, because my example is R4, so when n is equal to 4, then what I have is I have a four of those vectors, E1, E2, E3, E4, and each one of them has four components. So E1 has 1, 0, 0, 0, 0. So 1 on the first component, 0 otherwise. E2, 0 on the first component, 1 on the second, 0 otherwise. E3, 0, 0, 1 on the third, 0 otherwise. E4, 0 everywhere, and 1 on the last component. Now, those vectors, they are the basis vectors in R4, and they are linearly independent. Consequently, if you give me any vector, I can write that as a linear combination of those vectors E1, E2, E3, and E4. So when I say I can write them as a linear combination, that means I can find alpha 1, alpha 2, alpha 3, alpha 4, such that if I sum those, I can recover this vector. So an example, if you have a vector of 2.0, minus 13, 5, and 2 over 7, then you are capable of writing this vector as a linear combination of those vectors by having 2.7 multiplied by the vector E1, minus 13 multiplied by the vector E2, plus 5 multiplied by the vector E3, plus 2 over 7 multiplied by the vector E4. So to see this, right, you can equate the left-hand side and the right-hand side in the following way. So when you multiply 2.7 by the vector E1, what do we get? We get a vector. And what's the component of this vector? It's 2.7 multiplied by every component of the vector E1. Meaning that it's 2.7 times 1, which will give you 2.7. Then you have 2.7 times 0, which will give you 0. Then you will have another 0, because it's another 2.7 times 0. And then you will have another 0, which is another 2.7 times 0. Similarly, for E2, if you multiply those together, you will get minus 13 times 0. So the first component of your result will be 0. Then you will get minus 13 times 1, which will be minus 13. Then you will get minus 13 times 0, which will be 0, and 0 as well. And you do the same for the other vectors. So now you would notice that the resulting vector will be 2.7 on the first component and 0 otherwise, minus 13 on the second component for the second product and 0 otherwise, 5 on the third and 0 otherwise, and 2 over 7 on the fourth and 0 otherwise. And now if you add those together, you will actually recover this vector 2.7, minus 13, 5, and 2 over 7. Remember, when we add them together, we add component-wise. So we will take 2.7 and add that, which is the first component of this product, and add that to the first component of this product, and this product, and this product. So you'll get 2.7 plus 0 plus 0 plus 0. So you'll get 2.7. Then you will get 0 minus 13, 0, 0. You'll get minus 13, and so on. Okay, so those vectors are called linearly independent because I cannot construct a linear combination to be equal to 0 unless the coefficients are equal to 0. And because they are linearly independent, I can write any vector as a linear combination of those basis vectors. So we call those vectors the standard bases in Rn. Here we call them the standard bases in R4. And they form a linearly independent collection of vectors or set of vectors. Of course, not all vectors are linearly independent. So here's an example where you have V1, V2, and V3. Now, you can clearly form a combination of those that will give you the 0 vector by picking V1, by picking alpha 1 to be 1, alpha 2, alpha 3 to be 1, and alpha 2 to be 2. So if you would do that, then you are able to say that V1 plus V3 plus 2V2 is equal to 0. I think there's a typo here. This should be plus instead of minus. So those vectors are not linearly independent. Why? Because I was able to find a set of coefficients, right, that will make this equal to 0. This linear combination of those vectors, I was able to find alpha 1, 1, alpha 2, 1, and alpha 3 alpha 1, 1, alpha 3, 1, and alpha 2, 2. And that's why these vectors are not linearly independent. Right, so now we're going to move to the next topic. We're going to switch gears and actually start talking about matrices. And matrices are really critical in machine learning, and they're very important to, all the dynamics that we do in machine learning. So if you're looking at MLPs, if you're looking at transformer models, they always involve matrix products or matrix vector products. So it's really a critical point to understand what a matrix is, how can we add matrices together, and how can we multiply matrices together. Right, so what is a matrix? A matrix is nothing but a table of numbers. This table of numbers has m rows and n columns. So a matrix of size m by n of real numbers will be a table of the following form. So this is a table, right? And it has 1, 2, 3, up to m rows. So that's why we say it's a m by n, right? And it will have n columns. So it'll have 1 column, 2 columns, 3 columns, up to the nth column. Okay. So this is a matrix which has a real value on every entry in it, right? So it will have real value for every entry in it. And those there are m columns, m rows, and n columns for those values. Now, to denote those values, I'm using the index A. I'm using A and 2 subscript indices. The first subscript is going to indicate which row I'm in this table, and the second index is going to indicate which column I'm in this table. So for example, if I am talking about the real values that exist in the first row, I will be saying I'm talking about A11, which is the real value that is in the first row, first column, or A12, which is the real value that is in the first row, second column, or A13, right, which is the A or the real value that is in the first row, third column, up to A1n, which is the value in the first row, nth column. I can do the same for the second row. So when I go A21, then I am talking about the value, the real value, in the second row, first column. When I go A22, then I am talking about the real value in the second row, second column, up to A2n, where I'm talking about the value in the second row, nth column. The same for the third, and the same for the last, where I'm talking about a M1, which is the real value in the mth column, mth row, first column, sorry, mth row, first column. A M2, which is the mth row, second column, up to a MN, which is the mth row, nth column. So notice that when we're talking about a row, first of all, we have a row vector. So remember our transpose notation, right? So that we represent that by a row, right? So if you want to refer to a vector here, you need to use this transpose notation. And across a row, the first index, right, is always fixed, right? So A, as you see, 1, 1, 1, 2. So 1 is fixed, right? In the second row, a 2, 1, 2, 2, 2n. And the last one, a m1, a m2, up to a m. I could do the same and talk about values in columns, right, instead of rows. So if I'm talking about the first column, you will see that the second index is fixed and the first index changes. So A1, 1 is the first row, first column. A2, 1 second row, first column, A3, 1 third row, first column, AM1 mth row, and first column. So notice here that the second index, 1, is fixed because I'm talking about the values, the real values that exist in the first column. Similarly for the second column, and similarly for the nth column. So if I'm talking about the values in the nth column, the second index will be n all the time, and I will be referring to the real values a1n, a2n, a3n, a2 up to amn, where m is the row, like I have m rows and n columns. Right. So this is a matrix. It's just this set of numbers that exist in a table, and I can index, those values in that table by using this two subscript notation, right? Where the first subscript corresponds to the row index, and the second is to the column index. In terms of notation, we're going to use capital bold letters to describe a matrix, right? So if I have big bold A, that means I'm talking about a matrix. And I'm going to be using the notation A belongs to R m by n to say that I have a matrix which has m rows and n columns, and the value in this row and columns are real numbers. So when I use a notation A belongs to Rm by n, right? Rm by n, then that means that my matrix has m rows and n columns. And each value in that row, in that matrix, is a real number. Okay? Now, there are operations you can execute on top of this matrix. And of course, so yeah, before that, here are some of the examples, right? So this is a matrix A, which is made of 4 by 2. So we know when we see this without looking at the matrix, we already know that, okay, this is a matrix which is made of real numbers. It has 4 rows and 2 columns, right? So 1 row, 2 row, 3 row, 4 row. So we have 4 rows and then a column and a second column, right? So that's R4 by 2. And each component here is a real number. And now you can refer, to values in this matrix using this double subscript notation. So for example, if you're looking at the value A32, then that would be A3, meaning you go 1 row, 2 row, 3. So third row, second column, 3, 2, which is minus 0.65. This is another example where you have a matrix V, which will have 3 rows and 4 columns. So again, we don't really need to look at this V to understand how it looks or what's the shape, because we know that if we write R3 by 4, it means that we are talking about 3 rows and 4 columns, right? And each component in those 3 rows, 4 columns is a real number. Okay. And you can again refer, to values in this matrix by this double subscript notation, right? So you could say if I'm looking at B sub-index 3, sub-index 4, that means I'm looking at the value of B on the third row and the fourth column, which is minus log 3. Okay. Now, of course, the m by n, right? This m and n can equate, right? So instead of saying 4 by 2, 3 by 4, we can define matrices, for example, of size 4 by 4, right? So now this is a matrix 4 by 4. Without looking at the matrix, we know its shape already. It'll have 4 rows and 4 columns. And now if m is equal to n, then we call that matrix a square matrix. Okay, so if we have a square matrix, it means that the number of rows is equal to the number of columns. Now, an important operation, right, that you can execute on top of this matrix is something we call transpose operation. So remember what we did with the vectors. We talked about the transpose operation, right? And then we said a transpose operation means a row, and standard column definition or standard vector definition is a column. And then once we apply the transpose, the column becomes a row. Now, in terms of a matrix, what the transpose operator will do is that it will swap rows and columns and columns and rows. So for example, if I start with a matrix A, capital bold A, meaning I'm in a matrix, it has m rows and columns, so it's in Rm by n. And then let's say I list the values A11, A12 up to A1n, or A21, A22 up to A2n for the second row, and the last row AM1, AM2 up to AMn. Now, if I execute the transform of the transpose operator, A transpose, then what I will be doing is I will be taking a column from this matrix and making that a row in the A transpose matrix, right? So I'm going to be taking the first column, A11, A21, up to AM1. Notice I'm talking about the column, therefore the second index is fixed, and the first index is changing. And now that column, because I transpose that vector, right, that column, it will become a row. So now if I transpose this column from A, which is made of A11, A21, AM1, now I will get a row vector, which is A11, A21, AM1, but in the row, not as a column. Then we do the same with the second column. So if you have A12, A22 up to AM2, notice again that the second index is fixed because I'm talking about a column. Now, when you transpose that, then you get a row, and that row is A12. So the same values, but now they're listed row-wise. So you will have A12, A22 up to AM2. So I took this, and then I just changed this shape, and I made it a row. Up to the last column, which is A1n, A2n, AMn. Now that will also become a row in a transpose matrix, whereby you take that last column from A, and then that will become a row in the A transpose matrix. So all this transpose operation is doing is that it's taking a column from A and then actually making it a row in A transpose. Or if you can think about it as taking a row in A and actually making it a column in A transpose. Okay? Now, what's the size of A transpose? If we started with a matrix M by N, then when you transpose it, you will get another matrix, remember, right? So if I transpose this, I will get another matrix. And that matrix will be made of N by N elements. So if you started with a matrix which has M rows and columns, then A transpose, right, will be a matrix, but that matrix will have N rows and M columns, right? So the number of rows here become columns there, and the number of columns in A become rows there. And this is easy to see, right? Because you're taking every column and making it a row. So how many columns I have? I have N columns in A. If every one of those columns is going to become a row, then I will have N rows in A transpose. And that's why you will get N here. At the same time, you have M columns, but every column becomes a row. Becomes a row, right? So that's why we get the N. However, we're also making a row a column in A transpose, right? And we have N rows in A, and that's why we will get M rows in A. That's why we'll get M columns in A transpose. Okay. So here's an example, right? Imagine I give you a matrix B, and that matrix B is made of R3 by 4. Again, we don't really need to look at the entries to know how this matrix looks, right? Because we can understand our notation. If I write R3 by 4, it means I have 3 rows and 4 columns. Each is a real value. So now this is an example matrix B, which is made of 1 row, 2 row, 3 rows, and 1 column, 2 column, 3, and 4 columns. Okay? So I have this B. Now, what about B transpose? Well, we can clearly know that B transpose, what shape it will have? Well, it will have 4 by 3. And then what is happening? You're taking every row and you're making it a column, or every column in B and you're making it a row. And for example, so here you start with the 0, 8, 2, which is the first column in B, and that will become a row in B transpose. You take the second, 2, 4 minus 0.65, and that will become the second row. You will take the third column in B3, 0.43 over 7, that will become a row in B transpose. You will take the last or the fourth column in B, 7 minus 5 minus log of 3, then you will get that to be the last row in this matrix B transpose, 7 minus 5 minus log 3. Or you could actually, decide to do it row-wise instead of column-wise. So the transpose operator works both ways. So you could take this first row in B, 0, 2, 3, and 7, and that will become a column. Or you will take the second row, 8, 4, 0.4, and minus 5, which is the second row in B, and it'll become the second column in B transpose. And now you see that your original matrix was 3 by 4, but B transpose will be 4 by 3. So if you start with a matrix M by N, and then you transpose that, then your resulting matrix will be N by N. Now, if you had a square matrix, remember, so a square matrix means M is equal to N, right? So that's what a square matrix is. So it's Rm equal to N, so it's our N by N, right? So for example, here we have a matrix C, which is made of 3 by 3. You can transpose those matrices, right? But when you transpose those matrices, your resulting matrix will still be a square matrix after the transpose, because it's M by M. And now if you make it, sorry, if it's M by N, and now you make it N by M, you will have 3 by 3. Of course, now you would need to transpose the vectors, right? Like, for example, the first column in C will become the first row in C transpose. The second column in C will become the second column in C transpose. And the third in C, the third column in C will become the third row in C transpose. However, their sizes will stay the same. You have 3 by 3, you'll end up with a 3 by 3 matrix. Okay? So now we understand what a matrix is, right? It's this table of numbers made of n rows, m columns. I can use this subscript, double subscript, in order to index things. And I also know how to do a transpose operator on those matrices. Okay. Now, what about addition and linear combination or linear operators on matrices? So, actually, sorry, before doing that as well, let's talk one more thing about symmetric matrices, right? So, so a matrix is called symmetric if its A transpose is equal to A. So upon doing A transpose of the original matrix A, if you recover the original matrix A element-wise, so if every element in A transpose equal to every element in A, then we call that matrix symmetric matrix. So for example, if you have a matrix which is made, how much is this? It's R3 by 3. If it's made of 1, 5, 0, 5 minus 2, 9, 0, 9, 91. And now if you transpose this matrix, so you will take the first column and make that a row, 1, 5, 0 row. You will take the second column, which is a 5 minus 2, 9. And in A transpose, it will become the second row. And then you will take the 0, 9, and 91, and then you will get that to be the last row, which is 0, 9, 91. You will notice that the matrix A transpose is equal to the matrix A on every element, right? So 1, 1, 5, 5, 0, 0, 5 minus 2, 9, 0, 9, and 91. So those two matrices are actually equal to each other. That's why we call this matrix A to be symmetrical. However, if upon doing the transpose, you don't get B to be equal to B transpose, then you don't have a symmetric matrix. So here's an example of that, right? If we have this matrix B, right, which is made of 1, 5, 0, minus 7, 2.39, and minus 12, 9, 91. Upon transposing that, you will notice that, again, how do we transpose? We know that. Take every column, make it a row. Then you would notice that the B is not B transpose. Consequently, this matrix is not symmetric. Okay? We know what a matrix is, we know how we can do the transpose, and then we said that if upon transposing a matrix, we get equality, we get the transpose matrix to be equal, right, to the original matrix, then we have a symmetric matrix. Otherwise, we don't. Okay, now we can switch to linear operators. So imagine I give you two matrices, right? So I give you a matrix A, which is made of M by N, right? And I can list the values, right? A11, first row, first column, A12, first row, second column, up to A1n, first row, nth column, right? And then I can list them all. And I give you also a matrix B, and then I can list it all, right? So I can list this matrix B all, right? Now, again, the same way, using my double subscript index, right? So I can go B11, the real value on the first row, first column in that matrix B, up to B1n, B21, B22, up to B2n, up to BM1, BM2, up to BMn. Now, when I say that you're going to do alpha A, right? So you're going to multiply, right, that matrix by a scalar alpha, that means the resulting matrix, or the result will be a matrix of the same size, right? We want to change the size. It's of the same size, but now each component of that matrix A is actually multiplied by alpha. So the result of alpha A, so like 2A, 3A, 1.5A, right, is going to be alpha times A11, alpha times A12, up to alpha, right, times A1n. The same for the second row. So you'll get alpha A21, alpha A22, up to alpha A2n, right? And so on to the last row. So you will get alpha AM1, alpha AM2, up to alpha AM. Okay? So notice all that happened when I did alpha by A is I multiplied every component in that A, right, by alpha. Now I can do the same with beta B, right? So if imagine I have another constant beta, like, some real value, and then I decide to multiply that by B, it's the same thing, right? So it'll be just a matrix, right? Oops. It'll be just a matrix where now you will have beta B11, beta B12. So I'm just multiplying beta, right, by every component, right, in that vector, in that matrix, sorry. And then up to beta A1n, B1n, sorry. And that's an n. And then the last term, or the last row, will be beta times B M1, beta times B M2, up to beta times B Mn. Okay? So if you are multiplying a scalar by the matrix A or B, all you're really doing is multiplying every component in that matrix by that A and by that alpha or beta. Good? Okay. Now, can we add those two together? If you have the same sizes, right? So if you have the matrix A and the matrix B to be of the equal size, so number of columns and number of rows are the same in A and B, then yes, you can add them, and then the addition happens element-wise. So the addition will be element-wise, meaning that I will take the first component from alpha A, so the component on the first row and first column of alpha A, and then I will add that to the component to the first row, first column in the beta B. I will take the second component in alpha A, which is the component on the first row, second column, and then I will add that to the first row, second column in beta B, and so on, right? So if you add them together, you will get a matrix with the components of this matrix being the element-wise addition of every component of these two matrices. So that's how we can do a linear operator or add, two matrices together. Okay, so for this operation to work, we need to have the same sizes, but now this addition is happening component-wise. So the first term is alpha A11 plus beta B11. So we multiplied alpha, because we're looking at alpha A plus beta B, right? So we multiply alpha by A, meaning we multiply alpha by every component in A. We multiply beta by B, meaning we multiply beta by every component in B, and then we add element-wise. So you will have alpha A11 plus beta B11, then you will have alpha A12 plus beta A12, up to alpha AMN plus beta MN, plus beta BMN. Now, Please notice that for this operation to work, the matrices have to have the same dimensionality. They need to be of the same size. So A and B, they both need to be Rm by n. Again, notice this notation. We understand this. A is in Rm by n, meaning it has real values, m rows and columns. B is the same. It's also in Rm by n. It has m rows and columns. Okay? So you can execute this as an exercise, and please watch out for any typos or any mistakes. There are some we did unintentionally, but there are some that we have done intentionally, so that you can kind of follow and then maybe let us know in the comments if we have some mistakes. So here you are doing alpha equal to, so 2a minus 0.5b, so you're doing 2a plus minus 0.5b, which is minus 0.5b. And now you can execute this like we just said here, right? So you will multiply 2 by every component on A, and then you will multiply minus 0.5 by every component in B, and then you will do element-wise addition. So please make sure that those calculations are correct, but the idea is that we just are doing the same thing we wrote here, but with real numbers, where we take 2 times A, so 2 times 7, minus 0.5 times 3, and then we add them together. Okay? So that's about matrix addition and linear operators and matrices. What about matrix multiplication? So imagine I give you two matrices. So I give you a matrix A, and I give you a matrix B. The matrix A, it will have a size of m by n. So I will tell you that this matrix A, it has Rm by n, meaning it has m rows and n columns. And the matrix B is n by p. So that matrix B, it will have n rows and p columns. Now I will attempt to do a multiplication, right, of these two matrices. So I want to multiply a matrix, right, which is made of m rows by n columns. That's matrix A. And I want to multiply that with the matrix B, which is made of n rows and p columns, right? So that's the matrix B, okay? All right, so imagine I want to do this multiplication. Now, this multiplication is only allowed, right, if the number of columns in A is equal to the number of rows in B. So if your number of columns in A is equal to the number of rows in B, then you are allowed to execute this multiplication. If the number of columns is not equal, then you cannot execute this multiplication. So if the number of columns in A is not equal to the number of rows in B, then you cannot execute this multiplication. So if I give you a matrix A in m by n, it will have n columns. And if I give you the matrix B in n by p, then I will have n rows. Because the number of columns and the number of rows, the number of columns in A and the number of rows in B are the same, then I can do this multiplication. However, if I was doing m by 3, right, or m by n, which is n equals 3, and B is like 2 by P, then I cannot execute that because the number of columns in A is not the same as the number of rows in B. Okay. So to do a product of the two matrices, the two matrices does not have to be of equal sizes, but they have to have that the number of columns of the first should be equal to the number of rows of the second. Okay? Yeah, sorry about that. I'm a bit ill, I think. I'm getting a cold. Okay, now, the resulting matrix C of this product will have a size. So, of course, when we multiply the matrices, the result of this product will also be a matrix, right? So the result will also be a matrix. And the size of that matrix will have the number of rows to be equal to the number of rows in A, and the number of columns should be equal to the number of columns in B. So when we multiply two matrices, we need, first of all, that the number of columns of the first to be equal to the number of rows of the second. And the result will be a matrix as well, with the number of rows being the number of rows of the first matrix in my multiplication. And the number of columns will be the number of columns of the second matrix in my multiplication. So if I am multiplying A, B, which I call a matrix C is the result of this multiplication, this will also be a matrix. However, this matrix will have a m rows, right? So it will have m rows, which is the number of rows of the first matrix, and it will have p columns, which is the number of the columns of the second matrix B. So the matrix C is going to have m rows, the same as those in A, and p columns, the same as those in B, because I'm executing A-B multiplication. Okay, so now I can list the entries in this matrix C. So this matrix C will have C11, the value on the first row, first column, up to C1P, which is the value on the first row, pth column. Why pth column? Because I'm doing the multiplication. So we know that these are equal, so I can execute the multiplication. And now the result will be m by p, number of rows of the first, number of columns of the second. And that's why I have p columns. Okay. And then here we have C21, C22, C2J, C2P, up to CM1, CM2, CMJ, and CMP. Now notice that I additionally listed for you a row I, so I call that CI1, CI2 up to CIP, which is the row I in this matrix C. And I also listed the column J, which is C1J, C2J up to Cij and CMJ, which is the jth column in this matrix C. So notice that I'm talking about a row I does not change the first subscript. I'm talking about the column, the second subscript does not change. Now, how do we compute the components in this matrix C? So we know that we can actually do the product if the number of columns in A and is equal to the number of rows in B. We know that the size of the resulting matrix is the number of rows of the first matrix in my multiplication and the number of columns of the second matrix in my multiplication. Now, how are we going to compute, right, the components of that matrix C? So how are we going to compute those components? So let's look about how we compute the component Cij, right? So how are we going to compute the component Cij? So the component Ij of the product of the matrix C, Cij, is located in the row I, jth column of that matrix C. How do we compute that? The way we compute that is by taking the ith row of the matrix A. So we're going to take the ith row of that matrix A, y of that matrix A, because that's the first part in my multiplication. And I'm going to take the jth column because I'm interested in the ij component. I'm going to take the jth column of my matrix B, right? So I'm going to take Cij to be the ith row of my matrix A and the jth column of my matrix B. So I'll take the ith row and the jth column. And then I will do the product together, of these two, and that will give me the value Cij. Now notice the following, right? So let's be careful here. This is a row vector. So this is like a vector. Let's call that A transpose, right? It's a row vector. And this And of course, I should say which row vector it is from this matrix. So some people, you might see they're actually doing this. They are sub-indexing it with I to say this is the row vector corresponding to the ith row in that matrix A. And notice that this is just a column vector. So this is like B vector, right? So that's B. Some people, again, use bold BJ to denote this. For us, it's not going to matter at this stage a lot, but just the idea is that notice that this involves a transpose by a column vector. What's that? That's an inner product. Remember, we took that in the previous lecture, right? We said that this U transpose V is an inner product. And we know how to compute the inner product as well. So we know that the result of the inner product is a real number, right? Because this is an inner product. So we know that to compute an inner product, right, we get a real number. And we also know that to compute the inner product, we will take the first component from the first vector, multiply that by the first component of the second vector, add to it the first component of the first vector multiplied by the add to it the second component of the first vector multiplied by the second component of the second vector. Add to it the third component of the first vector multiplied by the third component of the second vector, and so forth. So in other words, if you remember from the previous lecture when we talked about inner products, the inner product was a real number. The result of the inner product was a real number. So it was a value, wasn't a vector. And the way we computed this is we took the first component from the first vector, multiplied that by the first component of the second vector, and added to that the second component from the first vector, multiplied by the second component of the second vector, and added that to the last, and so on, up to the last component product. So then we take this and multiply by that. And we add everything together. So if you have this ith row of this matrix multiplied by the bth column of this matrix, right? All you're going to do is you're going to take AI1, multiply that by B1J, plus AI2, multiplied that by B2J, plus dot, 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 up to AIN, multiplied by BNJ. And then you could write that by the, you could write that in a summation notation, right? Now, notice this summation notation. Is there anything wrong with it? Maybe there is, right? So what I am writing here, does that equate to this? You can check it and let us know in the comments. Okay. Now, the idea is, so let's recap this slide because it's important, right? So if you have two matrices A and B, and you want to do the product of A and B, right? You can only do the product of A and B if the number of columns in A is equal to the number of columns in B. The result of this will be a matrix as well, which will have number of rows as the first matrix number of rows in the product, and the number of columns will have the same number of columns in the second matrix of the product. For a component in that matrix, Cij, if I'm interested to calculate the value Cij, right, i.e. the value in the product in the ith row jth column, it amounts to doing an inner product between the ith row of A and the jth row of the jth column of B. So Cij will take the ith row in A and the jth column in B. And the result of the inner product from our previous lecture is a real number. The way we compute the inner product, take the first component in A and the first component in the vector B that you're doing the inner product with, and add that to the product of the second component by the second component, third component, and add to the last component product by the last component. So as we showed you here. And that's how you'll get Cij. So in order to get Cij, we will take the ith row in the matrix A, we will take the jth column in the matrix B, and then we will execute this product. And notice, again, this is an inner product, and that inner product we know how to compute from the previous lecture. Inner product gives me a number. A addition of matrices gives me a matrix. Product of matrices gives me a matrix. Inner product between two vectors gives me a number. Okay? So here's an example. You could work through this. So if you have a matrix A, what's the size of this matrix A? It has a 3 by 2, right? So it's a 3 rows, 2 columns. Matrix B, it has 2 by 4. So it's a 2 by 4. It means it has 2 rows and 4 columns. The resulting matrix will have how many rows and how many columns? It will have 3 rows and 4 columns. The way you compute that is you take like to compute that you will compute the first entry here. You will take the so here we are trying to compute C11, right? So C11 means that I will take the first row in A, multiply that by the first column in B. That will give me this. And then you will take the first row in A, multiply that by the second column in B, and then you will get C12, right? And that's this component here. And then you will take and you will repeat this up to the last term. So you will take the last row in A, multiply that by the first, multiply that by the second. You will get this value when you multiply by -1, 1. You will get this value when you do the inner product with 0, 1. You will get this value when you do the inner product with the third column in B of 0, -2. And then you will get this value when you do the inner product between the third row and the last column in B. So what have I done here? First of all, I noticed these two matrices, okay? They have the same number of columns and the same number of rows, so I can multiply them. I know their size because it should have a 3 rows as the rows in A and 4 columns as in B. And to compute every value here, I need to do the inner product between the corresponding row and the corresponding column, right? The corresponding row in A and the corresponding column in B. So here, for example, you can see that the first entry, C11, is going to do the inner product between the first row in A and the first column in B. C32, right? So C32 is going to do the inner product between the third row in A and the second column in B, and so on. So this is just like we described here, right? So to get any value Cij, I will take the ith column in A and the jth column in B. So all I'm doing here is I'm taking the ith column, ith row, jth column, and I'm just calculating the numbers, and I'm doing the inner product. So I take the 1, 2 row by that, that gives me this. And now if I want C12, so the value of the product in the first row, second column, then I will need to take the first row of A, second column of B, and do the inner product, and so on. Okay, so that's how we do matrix multiplication. Now, a vector is a special case, right, of a matrix. That vector, so if it's a column vector, right, it means that it's a matrix, but the second component in that dimension of the vector is 1. So for example, if I tell you 3 by 1, I have a B, which is in 3 by 1. That means I have a table, right, which is made of 3 rows and 1 column. So that's really a vector. And now, of course, you can multiply in the same way a matrix by a vector. But of course, the same conditions hold, right? So if you want to multiply a matrix by a vector, the number of columns of that matrix should be equal to the number of rows of that vector. And the result will be the number of rows of the matrix and the number of columns of the vector, right? Like the same thing we've done here, right? So let's go back. So if you have m by n and n by p, right, then let's say your p is equal to 1, because it's a vector. Now you need n to be equal to p, right? N to be equal to each other. So if I have n and n here, they should be the same. And the result will be m by 1, which is a table if p is equal to 1, which is a vector, sorry, if p is equal to 1. So now, if I am doing A by B, so a matrix vector product, notice that for this to be allowed, I need to have 1, 2, 3 columns in A. I need to have 3 rows in B, 1, 2, 3. And now the result of this will be the number of rows in A and the number of columns in B, which means that the result of this will be a 1, 2, 3, 4 by 1. So it's a vector of 4 by 1. So when you multiply a matrix by a matrix, right, A by B, you will get a matrix. But when you multiply a matrix by a vector, you will get a vector. How do you multiply? It's the same way we talked about here, right? So you would take to get the component of this resulting vector, you will take the first row and you do the inner product of the first column, which is B, right? So you will get this by this. That's the first component. And then that will give you the value. And then you would get the second row in A, multiply that or do the inner product with the vector B. So you'll get the second value. And you'll do the so forth up to all the rows. So you will get the row, the last row, multiply that or do inner product with the vector B, and then you will get this. Okay. Now, as an exercise, imagine you have 2 square matrices, right? Such that so imagine, you'll have these 2 square matrices A and B. Think about 2 examples where that if you do A by B product is not the same as B by A product. So if you multiply A by B first and then decide to flip the order, you multiply B by A, you will not get the same result. And the second exercise, which you can also attend, imagine I'm multiplying by the identity matrix. So the identity matrix is 0 everywhere, except on the diagonal elements, I have 1, right? Imagine now if I multiply by identity matrix some matrix A, can you show that A times I is the same as I times A? So if you actually flip the order, you will have the same result, okay? So the exercise is get us a matrix, 2 matrices A and B, such that if you multiply them, A by B is not the same as B by A. And that's to teach you that matrix multiplication is not the same if you do AB versus BA. However, it will be the same only if you multiply by the identity matrix. And that's why we ask you the second exercise to show AI is equal to IA. Please write your answers in the comments, and if you have questions, do that as well. Okay. Now, before I switch to talk about one more thing in this lecture, which is the neural network, right? Let's just do a recap of what we described so far, right? So we talked about a matrix, right? Let's go back a bit. Yeah. So we talked about a matrix that it's this list of numbers, and we can index those numbers, right, by 2 subscripts A, I, J. We talked about the typical notation of the matrix, which is the bold capital letter A. And we said when we write A belong to R M by N means that I have M rows and N columns in my table or in my matrix. Then we talked about how we transpose a matrix. So we can take every row, make it a column, right? And that will flip the sizes of the matrices. And then we said that the matrix is symmetrical if its transpose is the same as the matrix. Then we talked about the element-wise linear operations you can execute in the matrix, right? So you can multiply alpha with every component in A, beta with every component in B, and then you can add them. If you try to add them, you will add them element-wise. The result of this is a matrix, okay? And of course, for this to work, we needed to have the matrices to be equal dimensions. Then we talked about the importance of multiplication. And then we said for you to execute multiplication, we need to have the number of columns in A equal to the number of rows in B. And importantly, we said that the result of the product is another matrix. The matrix has the same rows as the first and the same columns as the second matrix in the product. To get the components in your matrix, all you need to do, if we're talking about an ij element of the product, we take the ith row of the first matrix in my multiplication, do inner product with the bth or with the jth column of my second matrix B in this example. And then we gave some examples here. And now we said that if you multiply by a vector, the result will actually be a vector. And the vector is a special case of a matrix where the number of columns is equal to. To get the component of a matrix vector product, you will have to do the same. You will take the inner product of, for example, if you're interested in the component 1, 1, you will take the inner product of the first row in the matrix, multiply that by the vector, or do the inner product with the vector. Second row with the inner product with the vector, you will get the second component of that vector, and so on. Okay. And then we had an exercise where you can find these A and B and try to tell us some examples of A, B is not BA. So to signify that the order by which you multiply matrices actually matters. It's not like numbers. It's not like real numbers. Only when you multiply with identity matrix, you can actually flip the order. Okay. So, okay, we talked about matrices. Right, where is this important, right? So why is this even important? Why is it useful, and and so on. So we're going to take an example of this that we see in machine learning, right? And see how we can use the matrix notation or even the matrix vector product notation to be able, to write those things. Okay. So imagine you have a neural network, and let's say we are discussing the value between layer L and layer L plus 1. Okay. So this is a very simple neural network. So here you have nodes, and those nodes are connected to the second layer, layer L plus 1. And the arrows between them, it means that we have a connection between this node in layer L and this node in layer L plus 1. And then here, what you can see is that we have a fully connected layer. So every node here is connected to every other node in layer L plus 1, and the same for the last node. Okay, imagine we have that. So we have these layers in a neural network, and they are connected via the weights. So these arrows here, right, they have weights. So W11 is the connection of the first weight. Is the weight from the first node here to the first node here. W12 is the weight that is connecting the first node in layer L to the second node in layer L plus 1, right? So here I just see 1, 2, meaning I'm talking about the first node here with the second node in the second layer. So how does this operation take place, right? So imagine you have some input vector, so x1, x2 up to xm, right? So imagine I have, m nodes in my layer L, right? So I have my layer L plus 1. And I have m nodes in my layer L, and I have n nodes in my layer n plus 1. That's why you see the last weight is mn, WMN. So it's the weight corresponding to the connection of the mth node in layer L with the nth node in layer L plus 1. Okay? So imagine I have an input vector, which is made of x1, x2, x3 up to xm. It's just some vector. Now, how does this operation work, right? So what you're going to do, right, is you're going to pass x1 to the first node. You're going to multiply that, right, with the weight connecting this node with that node, which is W11. And then you will this is the output, the first output for the first node in layer L plus 1. The same for the second one, where you will get that x1 multiplied by W12. Then you will have x1 multiplied by W13, and then you will have x1 multiplied by W1n. So all I am doing is I'm multiplying the first component of my input by the corresponding weight that is connecting these two layers together. So here, W11 is connecting the first node in L with the first node in L plus 1. W12 is connecting the first node in L with the second node in L plus 1. And W1n is connecting the first node with the nth node in the second layer. Now let's consider the second, x2. Now x2, again, is connected with this and this and this and this. So how do you compute that? Well, here what is happening is you're multiplying W21, so the weight connecting the second node with the first node, so the second node in my layer L with the first node. And then we also have the W22 times X2, which is connecting the second node by the second node. And you have W23 second node by third node. So second node in layer L, third node in layer L plus 1. And multiplying W2n, which is connecting the second node, right, by the nth node in layer L plus 1. Right? So that's how when we do these neural networks, right, like these simple neural networks, that's how this execution happens, right? So we take the first component of my input and multiply that by this weight, and that will be on the output of this neuron before you do in nonlinearity, if you have any. Then you'll do the same with the second node, third node, up to the nth node. Then you'll take the second component, and you'll do the same thing. Now, notice the only thing that's changing, right, is that my weight indices are changing because these are, different connections between different nodes in layer L and layer L plus 1. And then, of course, we do the same. So now for the mth one, for the last component of my input, now I am considering the connection between the mth node in the first layer and the first node in the second layer. So that's why it's called M1, because it's the mth node in the first and the first node in the second. And then, of course, I multiply by that value xm and I add it. WM2 now is going to be the WM2 is going to be the connection between the mth node in layer L and the second node in layer L plus 1. I will multiply that by xm, so I will get xm_m2 up to xmwn3 and so on up to the last one, where I take the input on the last node in the first layer, which is m, and I multiply that by the nth node, right, on the second layer, i.e. the last node on my second layer, which is m. That's why I call it WMN. And then, of course, I add them together, right? Okay. So the resultant mathematical expressions from this operation between layer L and layer L plus 1 is nothing but looks like this, right? So on this output of the first node, it's going to be W11x1 plus W21x2 plus W31x3 up to WM1xm. Notice something interesting, right? This one here is the same for the first node, right? So now notice that W11 is the connection from the first layer, right? First layer, first node to the second layer, first node. This is from the second layer, from the first layer, second node to the first node in the second layer. And 3,1 is going to be the third node in the first connected to the first in the second layer. And of course, I'm just multiplying, the weights by the corresponding values. Okay. Now the same here, you have x1 w12, x2 w22, up to xm w2m, and those are everything, right, that is coming from to this second node here, right, like this and this, and this, and so on, right, and this. Right? So here you will get W12, right? That's this term, W12. You will get W22, right? You will get W32 up to WM2, right? And that's how this ends. Okay? And of course, the same repeats for the n. Now, what is really interesting is that you can actually write, this equation, right, as a matrix vector product. So this equation, right, you can write it as a matrix vector product between a weight matrix W, which is made of all those weights, W11, W12, W13 up to W1n, W21, W22, W23, W2n, right? So this row corresponds to the weights that are connecting 1, 1, so 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, up to 1n. So these are the weights that are going out of this neuron and correspond to this row. W21, W22, W23, W2n are the weights going from this neuron up to the last neuron. So it turns out that this operation we just described, which is doing, this linear operation of taking the input, multiplying that by the weight, and adding, all the other inputs by their weights, is nothing but a matrix vector product, which could be written as W transpose times X input, right, in this example. Okay? W transpose times X input. So meaning that if you want to actually do this two-layer execution of a neural network, you're really just executing a matrix vector product, with the matrix being the weight matrix and the vector itself. That's why matrices are important. Because if you are dealing with a machine learning application, like let's say a neural network, then you need to be able to do these forward passes. And the forward passes needs to execute these linear operators that we just described, right? Like this multiplication. And it turns out that you can write all this multiplication as in a compact form as a matrix W transpose times a input vector. So now I will end this lecture here, but I will ask you to, as an exercise, to actually show that these two are equal, right? So I am telling you that these two are equal, and now I'm asking you, could you prove that for me? Can you show that? Now, what do you do in order to be able to show that? Now you need to execute a matrix vector product. We know how to do a matrix vector product, right? Like it's easy for us to do a matrix vector product. We know how to do that, right? And for the matrix vector product to work, remember, we need to have some conditions. What are those conditions, right? And then we know how we can compute each entry in the resulting vector by doing an inner product, right? And as a thing to remember, don't forget, we have a transpose here before we do the product. So we have W transpose times X input. So that will change, right, this matrix. It will flip it. Then you can do the product. So do attempt this exercise, and then we can continue next time. But now in this lecture, we learned matrices. We learned what a transpose is. We learned how to add them and do linear operators on them. We learned what a symmetric matrix is. We learned how to do the product, and we applied that to a neural network between two layers, and to execute a forward pass between two layers, of course, before the execution of the nonlinearity in the neural network. But the nonlinearity will happen element-wise on this vector anyway, so it's not that big. Okay, so I will end this lecture here, and then I will see you next time. So with that, I thank you. Hope you enjoy and you're finding this useful. Please write us in the comments if you have any questions, and if you attempted the exercises. And also do like the video, share, and subscribe if you find what we are doing important or interesting. And I will see you next time. Thanks a lot.